Tiene la palabra el Doctor Honoris Causa Eduard Hovy. The floor is yours.
Discúlpame, no hablo español. Lord Rector of the University, of the National Distance Education University, dear colleagues, and especially new colleagues, welcome to your new family. You will discover it is an interesting family, especially because we are the only people who wear clothes from 600 years ago in our special occasion. Nobody else does this crazy thing. Ladies and gentlemen, thank you. It is a great honor to be here and to receive this degree on the 40th anniversary of UNED. You do a wonderful job here, especially in these difficult economic times. When there are so many people who have difficulty, it is important to keep knowledge and the idea of education standing strong so that there is something for them to look forward to lead them when they need to find a new path. I recognize your hard work. To Professora Felisa Verdejo, a colleague and very good friend, Felisa, thank you for the laudatio. And thank you for building here a very, very strong group in our field of language technology, an internationally known group that stands equal to anything else in the world and that does work that is leading many people all around the world, especially in the QA for MRE evaluations and some of the other research that is being done by Professor Verdejo and her colleagues. I'm honored to be here as one of your colleagues now in this formal way. And finally, I would like to say I'm also honored to receive this degree on the day commemorating Thomas Aquinas. He was a special man who was always interested in the question, who are we? What makes me as a human different and special? And that is something I think that we are all interested in, this question. And that is something that somehow brought me to doing my own research. And I would like to, I don't want to talk long, but I would like to tell you why I'm doing what I'm doing and where this interesting path leads when you take this path. When I was 12 years old, I was sitting at the dinner table with my father and mother and family, and my grandfather wanted to read the Bible. Now he was from Amsterdam, and he was a very strong traditional Calvinist. You read the Bible. You do what God says, otherwise the devil will kill you, will get you. My mother was a Christian Scientist. She liked the idea of reading the Bible, but she did not like my grandfather's interpretation. For her, God was love, everybody is equal, we are all inside God, there is no devil. So they started having a fight. My father was an engineer and an agnostic person, and he said, stop this fight. You cannot define God, you cannot define the soul, your talk is meaningless. There was a wonderful discussion which we children used to slip away, so we did not have to listen to the Bible reading. But as a result, the question came to me, what am I? How can I do something in my life to prove to my father that yes, I do have something special, there is a soul, or to prove to myself there is nothing like this? Can one in today's modern society look at the questions that also held busy Thomas Aquinas and use modern technology to investigate this question to see, can you prove something with modern computers? As a result, I studied mathematics, and then I went to study artificial intelligence, and I decided to choose natural language, human languages, as my area of study. Why? Because it is a wonderful window into your mind. If I ask you, you are an expert in your language. You have spoken Spanish since you were 2 years old. How many words do you know? How many words do you know in your head? You don't know. How many rules of grammar, how many syntax rules do you have in your mind? Can you list them? No. And yet any 3-year-old child can talk to you. They don't know, they just do this. Isn't that a wonderful thing? If you can take language and you can open up and see what is the complexity of language, and through that, what is the complexity of the mind, how can you understand what is meaning, what are you, maybe you can use the computer as your tool, a tool that St. Thomas never had, to figure out how can I prove something? How can I test it in the computer? That's what I tried to do. A small story. When I finished my PhD thesis, which Professor Verdejo showed the book there, the black book, I made a computer program to tell stories. And I set the parameters that it had some emotions and some things it liked, and it was speaking to somebody about a topic that was difficult, and the person who was hearing was an angry person, was a senior dominant person, had no time, had the opposite opinion, and my computer program chose to say nothing. And I thought it made a mistake. And I went, and for 45 minutes I checked every step, every line, and there was no mistake. The computer program had correctly reasoned that it is better to say nothing, step by step. And it was a surprise to me. I did not know the computer program could do that. So I thought, maybe you can build something that will surprise you and will tell you something more, something unusual, unexpected about the behavior of a complex organism through a combination of simple rules. And all my life I have been trying to do that, and now I'm trying to do that in a new way. So here is what I'm trying to do, looking at the complexity of the mind through the tool of the computer to see if there is a possible modeling. And I'm afraid to say I don't think there is very good news that I can see so far. But in the meantime, working in language technology, there are many, many, many useful things that people like Professor Verdejo and colleagues and people in my group that we build for you, society. In a field called natural language processing, or sometimes computational linguistics, or sometimes human language technology, it is a complex field with many different aspects. And one of the aspects that you know best and that you have used yourself is information retrieval. Surely you have used Google in the last 2 days. Yes? Have you ever wondered, how does Google work? Why does it work? What do they make the magic so that Google can work? Let me show you how simple it is. Let us take that article about Thomas Aquinas. You can count every word in the article. So you can make a long list and say so many times this word, so many times this word, so many times this word, right? You can rewrite that list as a little vector, just a list of the words and their numbers. And then you can do a magic trick. You can build a big internal structure inside the computer, a knowledge representation, a matrix, which you can think of as a vector space, they call it, as just something that has about 600,000 positions, one position for each word, and when you take any document, you put it in there, and you say, this document has this word so many times, and this word so many times, and so many times, and you can place it exactly in that space in its right position, and that position tells you how many words it has of each kind. You can see it there, right? Now you take another document, and you say, I have to go to UNED. How do I get there from the airport? That has different words. You can count those words, and it goes in a different part of the space because it has a different balance of words, right? Imagine if you write a computer program to go to the whole web, and every day and every week and every month look at every document you can find on the web, count all the words, and put them into this space. You have a very, very, very large data structure with 7 or 8 or 10 billion documents sitting in there, each one a little point. That is what Google has. Now, when you say, I want to ask my question, you type some words into the search engine. Those words get pulled out, some words are thrown away, and other words go into this little space, and they say, where are the documents that have these words? Ah, they are in this part of the space, or this part of the space. And so every document that is in that part of the space, in the central part, gets put out and listed and given to you. So simple is the core of what Google is doing. Of course, this took about 50 years of engineering. a lot of careful work, a lot of careful tuning and tests with people and parameter settings and lots of hidden things I cannot explain in time, but this is the heart of why it works. You take documents, you look at the words, you look at the statistical combinations of words, and you do something in something called a vector space with mathematical operations. When you look at machine translation, which is the second area of what we do, there the task is give me one language and change it into another language. And again, since about 1956, people have been working on this idea from linguistics and from machine translation and from computer science and from statistics, and have built systems now that work increasingly using statistical techniques, mathematical techniques, to find the balances. So many words from this side in this language go to so many words from that side, and this is how the words rearrange themselves. Again, with rather simple techniques. Let's look at question answering, a third area that we do. Professor Verdejo already showed you about Watson from IBM, that takes, to answer questions of the simple kind, takes thousands and thousands of computers, and through a lot of careful engineering over about 5 to 8 years, brought it down to 3 seconds per question. For instance, you have questions like this. If you look on the right-hand side, there is a question, which 4 countries does the United States not have diplomatic relations with? Which one is the most northern of those countries? There are 2 questions, one inside the other one. The computer has to take these words, break them down, find the countries, then go back to an atlas, find the most northern one. It has special purpose little reasoners for geography, for countries, for diplomacy, for emotions, for psychology, for many, many different things. And so there were different teams working on this, amongst others my own team, and we built an engine that goes into this complex architecture where you have to, from the left, get the question, break open the question, find possible answers through word matching from different documents, find evidence around these words for background information to put this in, balance all this information, count frequencies, how many times do I see this, how many times do I see this. Many, many operations that spread and get more and more and more and more options until at the end you have hundreds of thousands of possible answers, each one of them with different number balances, and coming down through careful engineering to one answer. That is how that system works. In each little step, it is not very complicated. It is just a lot of engineering to make all the steps work correctly. And again, it's just looking at words and how words combine. This little graph shows how, through engineering, things get better. If you look at the bottom line that goes like this, it shows when they began building the system in 2006, what was its correctness level? It was about maybe 30%. If you look on the right-hand side, it says, I'm 100% sure my answer is correct, and then I can only do 10% correctness. And then you can look one line up 5 months later in May, it had jumped to about 30% correctness. And then every few months the system got better and better and better and better, up to the point at the top where the little spots are. They show the correctness of the humans who answer the same questions. It is careful engineering with hundreds of people who sit and do work like this over and over that bring you things like Google, like translation, like question answering, like automatic text summarization, like speech to voice, to text recognition. When you talk into the telephone, into a computer system that listens to your words and tries to find out the text meaning, that brings you dialogue systems, information extraction, etc. There are about maybe 20,000 people around the world who do my area, who do this field, both in the research and practical side. And we bring you things like Google and like translation. And we continue to bring you more and more and more interesting technology. And all of this helps society, we like to think, and people use it. But the problem is, the systems are very simple. As I showed you, they're based on words. They don't work very well because they don't understand. Look at these examples. This is a classic example from machine translation. The spirit is willing, but the flesh is weak, was once translated in an early system by the vodka is strong, but the meat is rotten. Now you can see why the system will do that, right? Because it has word to word to word. But you can see the system is stupid. Why? Because it doesn't understand. Here is, in the bottom, a question-answer system. My own system, we built in 2003. We asked, where do you find zebras? And the answer was, in the dictionary. Why? Because there was some text that says, of so many thousand words in the dictionary, zebra is the last one, or something like that. It found in the dictionary, zebra, etc. And it is true. Zebra is in the dictionary, but it is not what you mean. How do you know what you mean? How does any child know that that question has a different answer? Why? That is the question that fascinates me. Somehow, we want to build into the computer the ability not just to match words, but to go into meaning, to go into understanding. And that is a different story. That is not an easy thing through a little bit of engineering and lots of hard work. That is something that requires large amounts of knowledge organized and structured into structures and reasoning on top of that, using complicated statistics perhaps we don't yet know, to give you more. I would like to show you one small example and then I will finish. If you go to try to work at meaning and to try to represent meaning in the computer the same way a philosopher would do, or a linguist or a mathematician, naturally you go to philosophers and logic, and you discover they have developed many theories ever since Leibniz and other people on how to represent meanings. But you discover those theories do not work when you try to build computers, because the basic units of meaning are not known inside computers. When I say water, I pick this up, I know it is wet, I know it is cold, I know I can drink it. When I say water to the computer, it just sees W-A-T-E-R. It has no knowledge about water. Somehow, we have to develop techniques to give background knowledge to the computer inside. How can we do that? Well, what we do now is we collect millions of words of text using Google and others, and we extract out the knowledge associated with water, and we put it into structures, and we try to refine those structures so that we can get more and more structured information associated with. For instance, if I take the word gas, I can discover there are at least 3 meanings of gas, and the one word has other words like price and octane and car, and another meaning has words like chemical and fluid and weight and molecule, and another meaning has poison and asphyxiate and breathe and gas mask, etc. Those 3 meanings are quite different meanings, and in the vector space they have quite different positions. So if I take a word and I put it into that same vector space, I can then say, well, how far is one meaning from another meaning there? There are my 2 little words, and I can then make the little red lines between them, and I can say this meaning and this meaning are close, therefore they are like synonyms, and this meaning are very far, therefore they have completely different meanings, and I can begin to find out the meaning connotations of every word, not just the small definition, but hundreds and thousands of words together. Well, my students and I and people around the world are building vector spaces and word lexicons with associated words in statistical ways like this. Most recently, the United States government gave us some funding to try to find metaphors inside text. Why? Because they are interested in looking at people who write Spanish and Farsi in Persia and in Iran, and Russian and English, to see what people are saying on the world, what metaphorical language they are using. So you say, can a computer understand metaphors? That is a very complex thing. Even we don't understand metaphor. Surely when I say the atom is like the solar system, that is quite easy. Yes, I can see the correspondence. But when I say this bloated bureaucracy is driving me crazy, there is a metaphor inside there, but how can the computer understand? How must it know that bloated, which means fat, big, and bureaucracy, which is a bureaucracy administration, how must it know these 2 cannot marry one another? They cannot be in a sentence. That was our challenge. Can the computer be made to understand these words well enough that it can do something like this? What we did is we break the sentence up, and we take the word family for every word there, and there are the words for bureaucracy and the words for bloated, and we ask, is there some connection between the word families? In the vector space, do the word families go together or not? In this extra set of words, in this meaning cloud of these words, can we fit them together? And through some careful engineering and many experiments to build our vector space, we used a network of about 200 computers for 4 or 5 days of billions of documents to build this big structure for each word family for each of them, can we find connections, and can we say that these match or do not match? And when the system runs, it comes at the end and it says, I do think there is a metaphor here, because bloated, which means fat and big, and bureaucracy, which is an authority, cannot fit together, and here are the words that I expect, and it shows you some information, and other words that don't fit together, and that says, here are my numbers, here are my statistics, I don't know if I'm correct, but this is my guess. Now, when I look at something like this, you can see the mismatch. When I look at something like this, I think, we would love to build computers that can not just do simple matching and make mistakes, but can go into some meaning and can begin to approximate what we do as humans, what the child does, very easily. But that is very, very complex work, very difficult work. People are now trying to do this all around the world by creating vector structures and complicated vectors called tensors, which we borrow from physics, and operations to combine the tensors together in such a way that we can begin to create an algebra of meaning, a calculus by which we can calculate how well meanings fit together inside the computer. This is an extremely exciting challenge. If we can do so, we will be the first to take meanings and the words associated with them and successfully put them on the computer and successfully create a calculus and algebra so that we can compute with them to create new meanings that match what the child will tell you naturally. And the child does not know how the child does it, but inside the computer we can open up the memory structure, we can look at the algebra, and we can explain why. I am very, very excited about this opportunity. I love my work. I love the students all around the world who are so excited to create something new. I hope that in 5 and 10 years' time we can bring you systems that do even better. And I hope ultimately we can go to people like Thomas Aquinas and can explain to them, you were talking about such complicated and difficult and deep questions. I don't know how to answer those questions, but I do know a little bit about what meaning is. I can go to my father and say, I don't know how to define what is God and the soul, but I do know a little bit about how to capture the meanings about people's usage and put them in tensor structures and compute with them and get answers that may be interesting to you as a scientist to look at. I think this is a very interesting point in our lives where we can take language, philosophy, logic, statistics, mathematics, and computers and marry them in one big multidisciplinary effort and not only answer deep questions for Thomas Aquinas, but bring systems like Google and translation and speech recognition to us, to normal human beings who do this work and who need computers all the time. Ladies and gentlemen, my Lord Rector, colleagues, thank you very, very much for this honor of the honorary degree. I hope that you have a wonderful day today here, my new colleagues, and I hope that you remember one thing. You are now doctor. In 3 months' time, nobody will call you doctor except your mother. Stay humble. When you are humble, your mind will be open for new challenges and new ideas, and that is the most important. Thank you.